Well, hi there, boys and girls. Today we're going to learn some derivative rules and a few special derivatives, at least when you encounter these special cases, what you should do. So off we go. We're going to start with the constant multiple rule, and this means that if you have a constant, like any real number, and it's sitting in front of some function, and you are intending to take the derivative of this, so we're going to have d dx, that's our notation for, I would like to take the derivative of this, then you can just let the constant sit there and then multiply that times the derivative of the function. Oh, I lost my pen. Back to my pen. There we go. There we go. And then if we have a sum and difference rule, and this is provided by the way that f is differentiable. F can't have any sharp terms, f can't have vertical tangent lines, and it has to be continuous. Alright, sum and difference. If you want to take the derivative of one function plus or minus another function, then this says you just take the derivative one step at a time. Just go right through there. So this would equal, I'm going to write down here, the derivative of f, and then plus or minus the derivative of g. I'm going to show you examples of these, so don't get too stressed out. So let's go through here and work a couple of them. Alright, so here I've got some information in the table, and I've got a as a function of f and g. It's actually f plus g. Then I have to find a prime at 2. This means I need to find the derivative of a and then plug in 2. So how I'm going to find the derivative of a is I'm going to take the derivative of f plus g, and so you can see that this is a sum and difference rule. So first of all, I'm going to find a prime. A prime is going to equal f prime plus g prime. You just take the derivative of each one. And so a prime at 2 would be f prime at 2 plus g prime at 2. And so we can go over here to the table, and here's f prime's column, and at 2 you can see that's 3. And g prime's column at 2, you can see that's 1. And our answer is 4. There it is. Now let's do another one. What about f minus g? Well, it's just the same thing. It's just sum and difference rules. So a prime is going to equal f prime minus g prime. So a prime at 4 equals f prime at 4 minus g prime at 4. And so we'll go over here to the table. F prime at 4 is 9. And g prime at 4 is 4, and so my answer here is 5. Now let's combine these two. What if I've got constants in front of f and g? Well, like I said before, when you take the derivative and you have a constant in front of a function, just let that constant sit there. So a prime is going to equal 3 f prime plus 2 g prime. See how those constants just sat there in front of the functions? That's the constant multiple rule. So a prime at 4 would equal 3 times f prime at 4 plus 2 times g prime at 4. So let's go over here and look and see from the column. F prime at 4 is 9. So we've got 3 times 9 plus, and then g prime at 4, well, is 4. So we've got 27 plus 8, so we've got 35. So we're good there. Okay, now here's a funny one. This is a quotient. You know, I didn't mention anything about a quotient at the beginning because this is a special derivative. If you have a quotient and there's a monomial in the bottom, then you need to separate it first. In other words, I want you to write f as x cubed over x plus 3x squared over x plus 2 over x. I want you to separate it out first and then simplify. So that's going to be equal to x cubed divided by x is x squared. 3x squared divided by x is 3x. And then we're going to write 2 over x as 2x to the negative 1 so that we can go through here and do our derivative. So f prime at x is going to equal 2x plus 3 minus 2x to the negative 2, which is 2x plus 3 minus 2 over x squared. And we want to find f prime at 1. So that's 2 times 1 plus 3 minus 2 over 1 squared. So that's 2 plus 3 minus 2. It looks like that answer is 3. And again, I want you to separate this every time you have a monomial in the bottom. That's a fancy word for only one thing in the bottom. If there's an x in the bottom and that's it, then you can separate it like this. Same thing here, except we're going to rewrite this second one as 2 times x minus 5 to the negative 1. Oh, an announcement. Great. Okay, hold on 1 second.
With a sponsor or a coach or on your way home. Please.
All right, we're back. I paused for some of that announcement anyway. Okay, back to this one. I want you to think about x minus 7 over 2. I don't want you to separate this one because this is just a number down here. You can think about this as 1/2 times x minus 7. And the other one we can have is 2 times x minus 5 to the negative 1. So just like with the constant multiple rule, we can take the derivative of x minus 7 and then just multiply that times 1/2. So f prime of x is going to equal 1/2 times, well, what's the derivative of x? Well, that's just 1, and we know the derivative of 7 is 0. Then we'll bring this negative 1 down, which is going to make that positive x minus 5 to the negative 2. So we can rewrite this as 1/2 plus 2 over x minus 5 squared. And we want to plug in a negative 1. So f prime at negative 1 is going to be 1/2 plus 2 over negative 6 squared, which is 1/2 plus 2 over 36, which is 1/18. So I have 9/18 and 1/18, which is 10/18, which is 5/9. Let me make sure I did that right. I'm going to actually change my fractions here. We're going to have 9/18 plus 1/18 is 10/18, and yes, that's definitely 5/9. I want to make sure I didn't make a silly mistake there. Okay, last example is looking at horizontal tangents. On your homework tomorrow, you'll actually find derivatives and set it equal to 0. But f has horizontal tangents every time f prime of x, or the slope, is equal to 0. So here I've got a graph of the derivative. These are f prime values. And f prime equals 0 right here, 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 and here. That's where f prime crosses the x-axis. And so that answer would be C. Now tomorrow on your homework, you're going to actually calculate f prime and set it equal to 0. And I will see you guys then.